Hello friends, Dr. Patterson again, and I am not ashamed to say that this is take number like 6 or 7 because I keep stumbling over my own words. So what I'm going to do in this video, I'm going to talk slowly so I don't mess it up again, is I'm going to cover the specifics of the components that we're going to use in lab this week and also the new commands for the week. But first I'm going to discuss what class is going to be like. And so the first thing to talk about is what each week is going to be. So the typical week in 1301, we're going to start on Monday, or really the lectures for the week will be available. There'll be a main lecture surrounded by questions. And so really this is meant like the initial set of questions are going to be all based on the reading content that is assigned each week. You should be able to answer all the questions if you've done the reading. Then there'll be my lecture video, which will actually be embedded in one of the quiz questions. Then there'll be another set of questions right after, some reading questions, some lecture-based questions. The point of this is, one, to get you to try to recall the information that you read about, reinforce it with a lecture that covers the same material, but hopefully with a little more context, and then ask you to recall that information again. There'll be other videos as well. So there'll be a wiring video. I show you how to create the circuit each week using, let's make sure you guys can see this, using the board's camera and the setup that I have here, or with the various simulators that I've developed for the class. And then I'll actually be posting videos that'll walk through the lab tests for the week as well. And these lab tests are going to be entirely to help you learn the material and how to interact with the devices that we're using. So if you want to learn the material and do well, which is on the next item, which is the quizzes on each week's material, you should do the labs. The labs are like setting the T-ball on the T-ball stand for you, and then hopefully when it comes time to take the quiz, you can do really well on it. It's not going to be the exact same problems, but it's going to be very similar content because you'll have to focus on creating the circuit and also writing the program for it, understanding the structure that goes into it, hopefully watching the videos that I post. You should do well on the quizzes. And I'm going to try to post code in multiple different languages to help add context or to add additional context to what we're doing in the lab and hopefully help you understand more of how all this works. And so, I mean, every week I will definitely do a MATLAB version of the lab. I will also do a version written in C programming language. And using another board that actually has a very similar form factor, I will hopefully also have time to write everything in Python as well. And so you'll be able to see how these different languages compare and hopefully, again, reinforce that content that you're picking up throughout the week. So that's what each week will be in mechatronics with me, Dr. Patterson. And the board that we're using, whether it's the Metro or the Arduino, again, apparently when everybody's at home, they want to learn this stuff. And so there's some shortages on some of the kits that we normally order for the class. You will end up with one of these two boards. There's very minimal differences. It's mainly around how the computer connects and communicates with the board itself, which we're not going to get into any of the specifics that you'd be able to tell the difference between those two. We're just going to focus on, again, how we connect from MATLAB to the board or program it using the Arduino IDE and C programming language. So both of them use the exact same chip. It's the Mega 328P microcontroller, operates at 16 megahertz. All the devices that we're going to use, or most of them will require, or not all of them require, but a lot of them require that we use 5 volts, which is what these boards operate on. The input that you can provide The safe range is anywhere from 7 to 12 volts. Alternatively, you can just plug in the USB cord. So if you want to supply external power and have it run on its own, which we'll be able to see it do when we just do the C programming side, then you can do that. Otherwise, you have to keep the USB cord plugged in so you can talk between MATLAB and the board. The maximum output from each pin on the board is only 20 milliamps. And so really the only things that we can turn on directly and power directly from the board are things like, which we'll talk about in a second, light emitting diodes, and some other small, fairly low power devices. You can't ask the board to output a bunch of current, which is like the amount of electricity going through whatever circuit you have set up. Otherwise, it's going to cause the board, the chip itself, to essentially likely lose power. If you do a crazy enough circuit, you could burn out the chip, which I have seen done before. It takes a little bit of effort, but it's possible. So don't try to draw too much through the chip. It can cause it to fail before it would otherwise fail by itself. There's 14 digital inputs and outputs. We'll mainly be focusing on pins 2 through 13. 0 and 1 are usable, but they're also used as serial communication lines, which essentially allow the chip to talk through USB and with the computer back and forth. So you can use them. It just requires that you pay a little more attention to how you hook everything up. And then there's 6 analog inputs over on the side, which are like measuring the voltage, measuring voltages so you can determine what different values are from sensors or other devices. So it's, again, not super complex. We'll go over the PWM part, which is pulse width modulation, starting next week. So 6 of these are PWM capable though, and it's all of the ones with either the dots next to them, or if you're looking at an Arduino board, the ones with the little tildes next to it. So in this case, it would be 3, 5, 6, 9, 10, and 11. And that's identical between these boards. It's the same ones that are available for pulse width modulation. The other thing that you hook up, either you're going to end up with one of these acrylic bases or like an injection molded plastic base. No big difference. You do want to sit the breadboard right next to it. And the breadboard is effectively like how you're going to construct all the circuits for the class. It's really simple, and I'm going to point this out with my mouse. The red and the blue lines on the side are all hooked together. And so all the circuits that we create in the lab are going to use, the image is flipped, so that's not helpful. All the red lines we're going to plug in the higher voltages to, so 5 volts or 3.3, or if we do something crazy with 12 volts, we'd be hooking it up to one of the red lines, either on this side or the other. And then the blue one, we're going to hook up our ground, or essentially like where all the electricity is flowing to. And so that would be hooked up vertically along here, just like you see in the image. Those lines are hooked up vertically. The ones in the middle are all hooked up horizontally, but they're separated by each side. And so over on this side, this row across the top, I could hook a wire into that and then hook another wire into it and to somewhere else, and there'd be a constant connection between those two. And so that's what these the rows across are good for, is if you need multiple components going to essentially the same connection point, you can easily do that with a breadboard. And then the other side is separated out, but it's also connected across each row, just like shown in the image. You can connect in those 5 spots on either side, and within that 5-spot range, you'll be able to connect other items to it, or on the other side of the breadboard. We'll be powering everything using different voltage supplies. So we'll either be using the power from the USB, which will be routed through the board, and we'll have 5 volts over here and 3.3, which we can select from. We'll see, I'm going to attempt to draw all the circuits. I was going to use programs to construct them, but to be honest, sometimes I change them, and we might as well draw them and keep them as accurate to the lecture as possible. So we'll be seeing kind of the voltage. Yep, I'm looking at the right thing. Voltage supplies, most of the time it'll be 5 volts that we're supplying. The ground symbols, which we'll see the flow of electricity go from 5 volts to ground, usually through some device. If you're connecting directly from 5 volts to ground, you are making a mistake, and you are probably causing your USB, the chip in your computer, to draw too much current, and it'll probably turn off your USB devices. Alternatively, over on the left-hand side, you might see a battery hookup, which is what we would get likely, or what we would effectively be able to get in the same way as we're plugging in a cord here. So voltage in, which would be right down here on the board. If you're supplying it with one of the battery supplies, which, give me a second. This desk back here is my collection of mechatronic stuff. It is a complete mess. We'll grab this one from now. So this is a 9-volt battery, but you might have gotten, you should get one of these. You won't get the 9-volt battery, unfortunately. You will get the connector that sits on top. And so you'll get this one, and you'd be able to plug that into that barrel jack. Or if you have, sometimes the kits come with like a 4 AA battery pack that you can put AA batteries into. You'll be able to supply with either one of those enough power to keep the board running if you need to. Again, that's only in the case of if we're going to be programming it with C or Python. The MATLAB programming language, the way it's set up with MATLAB, you can't actually disconnect the board and have the program continue to run. It's just it's one of those trade-offs. It allows us to use a programming language which you've already started to learn. Unfortunately, it like ties you to the computer while using your microcontroller. So resistors are essentially, it's like a way to constrict the flow of electricity. And you're trying to limit the amount of power going through most of the devices. And this is how we're going to restrict the amount of power or the current that we're trying to get out of those pins when we hook up the main device for the week, which is light emitting diodes. We're going to use resistors to limit the current that is capable of flowing through that circuit so that we can actually turn on the LEDs using the pins from the board. And then we get to light emitting diodes, and you might have noticed these symbols that I'm including on each slide. These are what they're going to look like when I draw them, or if my drawing's not crap. We're going to see these symbols for power supplies, different voltages, ground, resistors, which I always draw too few or too many of the angled parts, LEDs, with or without the circle. I'll probably do it without, and then switches as well. So each one has its own symbol, and the other devices that we look at will too, but it's just a simple drawing version that you can do to show what the circuit is. And so the light emitting diode allows us to essentially supply a little bit of current across the diode, and what happens is the electrons flow in, and they're, without getting too complex, it essentially causes it to release photons. So it's essentially releasing light. Also releases a tiny bit of heat as well, much less than like an incandescent light or even a fluorescent bulb. They're very efficient most of the time. And so it's also a very fast acting device, whereas with like an incandescent bulb, you turn it on and it actually takes a little bit of time to get up to temperature and emit the amount of light that it would. Fluorescent bulbs can take even longer. They're much faster than they used to be turning on, but it still can take a while for them to warm up and get up to full like power. Whereas LEDs, some of them are almost instantaneous, like nanoseconds for going from full off to full on. And so most of the time, you can't even see any variation in from when it transitions from on or off to on. And these will be the main devices that we're going to blink lights on and off this week to various tasks, along with the next item, which is a way for us to essentially monitor some kind of physical input external to the computer or Arduino board. And so switches are, you can get switches of all types and wire up a switch or something like a switch in many, many different ways. But these are essentially little push button switches where, and the correct symbol for this one is actually in the lower right, momentary switch. When you press it down, it's on. When you let go, it's off. There's also the switches which are more like you'd think of for a light switch, where you switch it on and it stays on, and that means that the circuit is actually closed. On means that it's carries across, allows the electricity to flow through. Just like with these push button switches, when I push it down, this would actually come down and contact those two sides and allow electricity to flow through there. So not too complex, right? Switches, lights, resistors, which limit the current going through the circuits that we're trying to create. But what we're going to do to control these or read values from them is two new commands. Let me talk about this first. So this sometimes helps people, especially those of you that are more mechanically minded than those that love electronics. So there's a good analogy between electricity and fluid flow. And if you think about fluid flow through a pipe, you've got water flows that flow from one location to another. And that's because there's some potential energy difference between those two, or in this case, a pressure difference between the inlet and the outlet. And then there's also the amount of water or other fluid flowing through the pipe. So it depends on that pressure difference through there, and also what are the losses in those pipes or other components that you're seeing. And then lastly, some of those components can be used to either put additional energy or work into the system or take it out. You might think about like a pump adding additional pressure or trying to help increase the flow rate, or a turbine, which would be trying to extract energy out of that system. Well, there's the same ideas for electrical systems. There's a flow through a circuit because there's a voltage potential difference from one end to the other. So if you have a battery and it's going, you have essentially a circuit that loops from the positive 12 volts to ground, you're going to see that potential difference in there, and it depends on which items you have hooked up. So there could be resistors or other wires or LEDs or motors hooked up that all have a resistance value and essentially can use up some of that current, or even limit the amount of current going through there, or the quantity of electricity flowing through those devices and wires. And then lastly, they can be used to do work, or in theory, you could also do work and add more in. But classic examples, we've got motors included in the kits, we've got LEDs, most of the things that we're going to control are actually extracting some of that energy out to do various tasks. And so it's the same ideas as what we had in a fluids-based system, we also have in this electrical system. It's just, that might have helped some of you. Doesn't help everybody because some people have no idea about pipe flows. So if this didn't help, just ignore it. It's cool. We'll learn more. So what I want to show you next, and I want you to get really familiar with the MATLAB documentation pages, is we're going to look up a few commands here, and I'm going to move a couple things around here so I don't break anything. We're going to look at a couple commands to control or read values from the devices that we're going to use this week. And in the initial video where I showed you how to hook up the Arduino board and test it for the first time, I already talked about one of these, which was a write digital pin. There's write digital pin. We can look that up. So this first one is write data to a digital pin on the Arduino hardware. And there's two ways to look at this. One is that this is a method on a class, the Arduino class. And so MATLAB gives you two ways to call this function or method. And one is to pass the Arduino as an object, which if we go back over to MATLAB, I've still got the Arduino hooked up and there's a communication line, or it's still established. We can double click on it and check it out. In theory, I think somewhere in here there's normally, it tells you if it's connected or not. Not important. But what we can do is test out these two ways of sending this write digital pin command. And so what they have is they have write digital pin. The first argument that they want you to pass is the connection to the Arduino hardware or the object that you have. And so in this case, the example that I used, it used A equals Arduino. So I have A as my Arduino object, which we can see up here in the workspace. And we have A, and it is of type Arduino. So it's an instance of that Arduino class. And then going back, we need to supply a digital pin number. Oh, there we go. Digital pin number, which is either a string, which is the double quotes in MATLAB, or a character array, which is the single quotes on either side. And then that's essentially letters, right? And or numbers. And then lastly, the logical value, which is going to need to be either 0, which is off, or 1, which is on. And so if we go back to MATLAB and I said, well, I could write digital pin and pass it the Arduino object A. And I'm actually I'm gonna clear all, and I'm gonna rename this to Arduino object and reestablish that connection. So now it's the same object. It's the same connection, or it's a new connection, but it's to the same board. But now I can send commands to that Arduino object. So I can say write digital pin and pass it. The first argument is the Arduino object. So I put ard object. The next one that I need to pass is the pin, and it has to be in a string format. So we can say D, I want to turn that one LED on again, so D13. And then lastly, I need to tell it the state, or an integer or logical value. So an integer, I'd have to supply 0 or 1. For a logical, I could supply true or false. And in MATLAB, the true is evaluated as 1, false is evaluated as 0. And this is actually what I did up here is this not symbol is allowing me to say it's the opposite logic to what I had previously. And so it goes between 0 and 1, or true and false. Oh, I swapped that. True is 1, 0 is false. So it's off right now, so let's turn it on. So we turn that LED on, and then we can also turn it off. And this is thinking more along the lines of this is a function, and I need to pass the Arduino object as one of the arguments, right? But there's also the thinking of like, I've got a connection to the board, and it is represented in MATLAB as this object, as this kind of complex variable or complex item in MATLAB that I can actually tell it to perform commands. And so I'm instead going to say ARD object, so my Arduino object, and then I'm going to use the dot syntax and say write digital pin. And so I'm literally saying this method or function on this object needs to be called. And so I'm saying, hey, Arduino object, write to your digital pin, and then I pass it the arguments that are next in line. And so I'm going to say D13 and 1. And this is usually the version that I'm going to use is the dot syntax with referencing it, or the object, and then the method that's being called on it, simply because there's a lot of reasons that I'll do it, but I think it's easier to think about. You're like telling the board to perform a command. And so it's like you need to give it commands, you need to give it orders on what to do next. And so that's why I tend to teach it that way, is simply because it's like, hey, board, I want you to do something. What's the command that I want it to run? And then what's the information that it needs to actually do that? So we can run that dot syntax again and turn it off, and we'll see that same behavior where we can turn it on or turn it off. Now the other one that, the other function that we're going to learn this week is read digital pin. So we've got a way to control an output. We can turn something on or off using that 0 or 1. And on the board, it's actually toggling the pin on the microcontroller. When you set it to 1, it actually turns it on to 5 volts. And when you turn it off or down to a logic value of 0, it turns it down to 0 volts. And so there's a little bit of a mismatch in terms of the numbers in this case, but you're supplying this different logic symbol or logic signal, and so you're getting a different voltage value out of those two states. 5 volts is on, 0 volts is off. So the other one that we can look at is read digital pin, which is this first one up here. Again, read data from a digital pin on the Arduino hardware. So I can click on that, and we've got a similar setup for what the function is. But in this case, we're actually getting something back. And so if we look at the read digital pin, first the input arguments, we've got down here, we need the Arduino object, and we need the pin that we want to read a value from. Now, when this reads a value from the Arduino board, we're going to get back exactly the same thing that we would want to write to another pin. We're going to get a 0 or a 1. And so in the case of 0, that means it's reading a signal that's effectively off. If it's reading a 1, that means it's reading a signal that's much closer to 5 volts. There's some gray area in between. Essentially, like it's 60-something% of the value above, kind of in between, you'll get a high signal, and then everything below that, you'll get a low signal or off. We're just going to worry about on and off for now. And so everything essentially that's 0 volts will be read as a 0, and everything that's read as 5 volts will be read as a 1. So what we can do is then go back over to MATLAB and say, well, I want to read digital pin and pass it the Arduino object and say for pin, oh geez, let's read on pin 8. I don't have anything hooked up at the moment, so it's going to be a little weird. We'll do pin 8. And that's all we need to supply is those two arguments. And what it'll read back is the answer, right? And so we could even say pin 8 signal is equal to read digital pin and pass it the Arduino object and pin 8. And then now stored in that variable pin 8 signal, I've got whether it was a true or false. If I wanted to have it show up as true, I'm going to grab a resistor here just for this example. And I'm going to plug this into 5 volts over here. And then one end of the resistor. And then in the other end of the resistor, I'm now going to plug it into pin 8. And so I'm essentially trying to make sure I'm limiting current as needed. And then I can say read that again, and I get a value of 1. If I were to unplug this again, and just let it kind of dangle there. Let's see if it continues. Don't touch the board. Let's run it again. And now I get a 0. And we can use the same dot syntax that we did earlier. I can say for that same thing, if I wanted to just pass it the pin value and more think along the lines of, hey, board, I'm talking to you. Arduino object dot read digital pin. And I get a 0, and then I can plug that in again and read it, and I get a 1. And so in this case, I could, if I wanted to modify this code up here, I could say, forget about the LED state. Well, let's write it to a 0. And then instead of this, we'll say LED state is equal to a dot read digital pin. And I'm going to read from pin 8. And that's all I need to pass it. So what I'm doing in this loop now is I'm first initializing a variable to 0. And then I'm writing that variable to a pin. And then I'm reading a new value from pin 8. And then I'm going to use that to write to the LED. Right? So I'm going to cycle back through over and over and over again. And a better structure might actually is probably this. So reading first and then writing. And then what we can do is maybe pause for 1/10 of a second. And instead of doing it 10 times, I'm going to do it, let's go for a while, 1,000. And so if we run this, what did I do? Oh, I'm not using A anymore. Let me grab that Arduino object name. There we go. So it's on. If I unplug it, it turns off. Plug it back in, turns on. Unplug it, turns off. There's a little bit of a delay. It'd be faster if I had a pull down resistor, I imagine. But now we can see that we're grabbing logic from some other state or from some other scenario and then writing it to the pin. And it should, oh, that is surprisingly slow. There's different reasons why it could be going slow. If I add, let's go like this. Oh no, it's not going to work well. Forget it. We'll fix it next time. Good enough for now. If we plug it in, it turns on. If we unplug it, it eventually turns off. We'll fix the speed thing in the next video. That's all I've got for this one. So make sure, because this is now going to be embedded in the middle of quiz that you work through. Make sure you listen to this, and then you should be able to answer all the questions. See you in the next video.